Hi, in this mini lecture I will introduce 1-bit memory element using a practical example of a lift button. It is a push button installed in the lift. It is a monostable one. You have a spring under the button. The button returns to its default position, open position when you release it. And in the default position means logic 1 because of this pull-up resistor, which forces 1 high voltage to this input, and if you press it, you simply ground the signal and produce 0. And let's assume that 0 will mean no light and 1 will mean that the light is on. And imagine that you enter the lift and you note down the input and output. So you can see that the X, so I mean the push button, is in its default position, which means logic 1 on input X. And no light is present on the output, under the button, no light. You press the button, simply you produce logic 0 on input X, and you can see that the light is on. Okay. Then you release button after choosing the target floor. So you again get 1 on an input X, but you still see the light. Okay, the light is still on. And now let's compare these two rows and interpret them. It is a quite new behavior. Okay, for the same value of X, you get two different values of Y. So Y must depend not only on X. Okay. There is a memory element inside. In this case, 1-bit memory is enough. 1-bit memory. In this memory, the event of pressing the button for the first time has been stored. And that's why Y is the function of X and also of 1-bit memory. This 1-bit memory. Let's imagine you reach the target floor, and what you see? You see that the light has been switched off. So you must have another input in the system that is used to switch. You cannot do it using this switch. So there is another input which is connected to the lift position sensor, which produce, let's say, 0 signal when you reach the given floor. And this signal switches the light again off. And what it means that this input is used to set the memory in logic 1, and it is called S input. And this input will be called, or is called R. It is reset. It returns the output to be 0. And because they are active low, because 0 sets 0 on S, sets output to logic 1, and 0 on reset resets the output. So to denote it, to show it that they are active low signals, you put dashes, you complement bars above S and R. And also to have it labeled in a standard way, the output of this 1-bit memory element is called Q. What's inside this element? Inside there are only 2 gates, 2 NAND gates. However, they are not connected in a way that was used, yes, in a straightforward way, which are used in combination devices. They contain the feedback connections. Look at this, and the output is connected. Feedback is fed back to the other gate, and the same is true for the lower gate. Okay, and is also standard way to have two outputs of the two gates outputted. One is denoted by Q and the other by not Q. And this is called SR asynchronous latch. It is the simplest 1-bit memory. The practical 1-bit memory contains two gates, and it is asynchronous, not having clock. In the real device, in majority of systems, sequential systems, you've got also clock that allows operating or disallows operating of the given block of the synchronous system. So let's now derive synchronous version of SR latch. Simply to make it working, to make it work in only when the clock is equal to 1, you simply gate the signals S and R using clock signal. If clock is equal to 1, the signals SR are transmitted. Okay, not S, not R. But in order to have a positive logic, I mean the active high signals, we should use NAND gates to invert these signals, to have them not S, not R, and use well-known asynchronous device, asynchronous latch, which is also constructed using NAND gates. And currently you've got SR, which is the active high version of the latch. And at the same time, it is synchronous one. So it can operate only when CLK is equal to 1. If CLK clock equal to 0, don't change anything. Don't change or don't work at all. Don't change output. Q is in front of S, not Q is in front of R, and that's all. It is a 1-bit synchronous latch. And latch is the device which is triggered, or which is allowed to operate, it is allowed for operation when the clock is 1 or when the clock is 0, so depending on the solution. Let's describe its operation in truth table. A truth table will contain SR and Q of T. What means T? You must consider these all gates as having non-zero propagation time. There is a delay in each of the gates inside because it is physical device, so it takes time to react to the change on the input for each of the gate. So now let's put all the combinations of the signals, these signals. Okay, the clock is not present in this table, and this table is not named, not called truth table, but state transition table. STT for short, STT. And what's the state? What does state mean? The state is the value of the memory. State is the same, is the synonym as memory. Memory content or value is the given state. So 1-bit memory can be in state 0 and in state 1. So this is the state signal. This is this one. And this is state transition diagram, transition. And what about Q of T? It is Q of T must be followed by delta t, which is this propagation time. Okay, so q of t means the current value of q, and t plus delta t means the next value of t after transients has passed. So SR00, what means? This S00, if the clock is 1, it is allowed to operate. So you've got 0, 1, 1 here. 1, 1 here means don't change anything. So you are in the same state as before. It is a memory command. Don't change anything. So the next state after delta t, after propagation time, will be the same as the current state. 0 or 1, depends. R1, it is an active high, so R1 means reset. This is active high, set 1 means set, means 1 on the output. And these two commands are reset. So put 0 to the memory. This is set. Put 1 to the memory. Okay. Store 1. And this is not allowed. It is not allowed. It doesn't make sense to set and reset in the same time. So don't do it. Never, please. Don't put. Okay. If you use it, don't put 1 1 on the inputs, on these inputs. So these two commands, reset and set, don't depend on the current state. The only command which depends on it is 0 0. So store it. Don't change anything. If you have 0, there will be 0. If you have 1 on the output, there will be 1 after delta t. Okay, thank you.